Okay, I think we'll get started here. So, hi everyone. Thank you for joining today's webinar from Miovision and DRMP. This is Matt Denick here from Miovision, Director of Product Marketing. Today we're going to look at improving mobility through active arterial management. And this is a use case of how DRMP uses automatic traffic signal performance measures to help Escambia County in Florida achieve that. So a couple of housekeeping items here before we get kind of rolling. If you have a question at any point during the webinar, feel free to enter that into the chat menu or chat window. I have my colleague Brent Merswolk here who is monitoring the chat window for any questions that might come in, and we will address all the questions towards the end of the webinar. And if you have anything for Sam specifically, just say question for Sam, and you can kind of go through that way. So again, very happy to have everyone here join us today for a really nice webinar and a discussion on how DRMP, a traffic engineering firm in Florida, has used ATSPMs, so automated traffic signal performance measures, to help reduce congestion with Escambia County. On the left-hand side from Miovision of your screen there, you have myself, Matt Denick. I'm Director of Product Marketing, and I'm joined by Sam Campbell from DRMP, who's a traffic engineer, and we'll do a bit of an introduction once we get through some of the intro content here. And Sam has an opportunity to go through really what made his engagement with DRMP or through DRMP with Escambia County successful. So housekeeping items out of the way, the agenda, what we're going to be talking about today is how really the importance first of traffic data and how that's a foundational element into building out your ATSPM strategy and how you use analytics to really just manage the health of your intersections and your network from an efficiency perspective. We're going to talk a little bit about a recent campaign that we introduced here at Miovision called Clear Signals, where we really wanted to lift the veil on ATSPMs and make them easy to understand and really show you where you can get started. We'll talk a bit about DRMP, and Sam will kind of run you through the case study of how DRMP is working with Escambia County to help them use ATSPMs to reduce delay, to reduce fuel costs or maximize fuel cost efficiency, and also from a vehicle emissions perspective, really manage all of that through active arterial management. And then we'll get into, throughout the way, a couple of poll questions where the folks on the line, we actually want to get your thoughts on where you are with ATSPMs and generally how you're incorporating those analytics into your strategy to create clear signals and really create efficiencies across your traffic network. So I like this stat. I always like kind of starting out with a really impactful stat, and I think this is something that leads into a lot of the results of previous poll questions that we've had from ATSPM-based webinars, where this was a survey of municipal planning organizations across the US, where they identified that data is the most significant barrier to using performance measures, and that 64, nearly 60% of MPOs surveyed said that, well, it's the number one, data is the number one obstacle from actually them being able to expand their use of performance measures. And I think this is pretty interesting when you consider, at the foundation of using analytics and really using performance measures is data. And at Miovision, that's what we're focused on. We're really focused on empowering cities with data, with traffic data, to help them make smarter decisions on managing their network. And just to recap from a previous webinar, this was some results of how familiar folks are with ATSPMs in general. And as you can see, a lot had responded that ATSPMs are new to me, but they're actually on the webinar to see what they're all about. And a few folks, nearly 40% of respondents also said that they're learning and they plan to start using them soon. So there's quite a few who we're kind of in our infancy in terms of how agencies are using analytics and performance measures to create efficiencies across the network. And I thought that was a pretty interesting stat. So first, I'll talk a little bit about where ATSPM data comes from. And so there's a couple of really core areas when we think about data coming into the system. And so the first sort of point is that data in isolation, it's just noise. We've heard from a lot of agencies and a lot of customers that it's not that they don't have access to the data and that they don't have the data they need, but it's actually taking that data and adding context to it to create something meaningful, something that unlocks intelligence, it's actionable. And so where performance measured data fundamentally comes from first is there's signal status from the actual traffic controller itself. So this is where phase interval data is coming from, timing plan information, phase termination, also things like time-space diagrams. And when combined with detector activations, we get some really interesting metrics around split failures, split trends, occupancy ratios, Purdue coordination diagrams, arrivals on green, red, pedestrian delay, yellow and red light behavior, all of those things. Detector activations on their own will give you things like volumes, and those are really important inputs into ATSPMs, both pedestrian volumes, vehicle volumes as well, and also pedestrian call button usage is another example of where we get there. Another really important element of identifying and measuring the impact of your ATSPM strategy is looking at before and after case studies and before and after examples using these metrics and analytics to see if what you have done has actually moved the needle in terms of making your network more efficient. So Wi-Fi MAC address data is a key component to building out and understanding things like travel time and speed, doing corridor congestion scans, providing data and analytics around travel time index, and also the reliability of that travel time. So that's where the data comes from. One example that we're going to look at today is the Miovision solution called SmartLink, which provides really easy to understand through the TrafficLink portal, really easy to understand ATSPM metrics. So this is the example that we'll look at today. And interestingly, it's also the reports and the technology that DRMP with Escambia County is using. So we kind of know where the data comes from. What are ATSPMs typically used for? And there's a number of objectives that are sort of centered around signal timing. And when you think about ATSPMs, it's about enabling that high resolution data to get a comprehensive really view into the performance of the network against your objectives. So many of our customers, agencies will look at maximizing arrivals on green. They're looking at using ATSPMs from a signal timing perspective for queue management. Maybe they want to minimize pedestrian delay, or perhaps they're optimizing for maximum throughput. They want to make sure that the efficiency of their corridor is the greatest that it can be. Traffic calming and safety, we're seeing a lot of focus and an increased shift into lots of interest around those areas. And then also minimizing delay along the corridor. But fundamentally, when we think about multimodal traffic, it's about providing equality for all road users. And when we think about that, it's about reducing complaints from not only drivers, but also pedestrians, anyone who happens to use the infrastructure. So this opens up our first poll question. Given that we walked through a couple of examples, which of the following best describes, so my colleague's just going to put a poll up here. So the poll's open. So which of the following best describes the objectives of your agency? And so there's a couple of examples here.
All of the above.
All of the above, yeah. So, creating safer streets, reducing congestion, reducing emissions and improving air quality, operating more efficiently, or all the above. So give you a couple of seconds to answer that poll question, and then we'll take a look at the results. Okay, let's take a look. All right, so yeah, so that's very interesting. I mean, it looks like when it comes to any one specific area, it's not. It happens to be all of the above, and so it looks to be centered around reducing congestion as well as sort of the next highest. But yeah, I think that really is the feedback that we get from a lot of agencies, is that it's really about using, ATSPM data and analytics are being used to reduce congestion, help you monitor and manage, and report on that return on investment, and really just verify the results of your signal timing operations. So thank you everyone for answering that poll question. So I'm going to get into a bit of some of the use cases for healthy signalized intersections and what does that mean. And then we'll give you a really cool example of an optimization example from a town here, a Miovision customer in Milton. And then I'm going to kick it over to Sam to walk us through the work that DRMP is doing with Escambia County. Fundamentally, signalized intersections and corridors, in order to be healthy, they really need to look at evaluating the performance on 3 levels, and that's typically maintenance, operations, and optimization. And you'll see kind of the fourth cog in that wheel is safety, And that's one of the elements that we obviously wanted to see if that's an area that you're looking to use ATSPMs as well. So not only are all of these important to achieving healthy intersections, it also makes sure that it remains that way throughout the passage of time so that it's consistent. So maintenance is really about helping unlock the efficiency of your traffic team and responding to citizen reports a lot faster. Operations and optimization is also about, keeping the efficiency of the corridor up, and then optimization is looking at ways that we can optimize the actual, not only progression, but optimize the throughput or output of the intersection and of the vehicles that are moving through it. So this is an example of an operational example. So with this case study of ATSPMs, we worked with the town of Milton, which is a small but mighty town close to Toronto, not too far from our headquarters here in Kitchener in Canada. So we deployed 15 intersections across the town of Milton, and we've been one of the more active customers in implementing ATSPM-based changes. We've done a number of sort of case studies and looked at a couple of examples with Milton. So the first thing that they wanted to do is they wanted to actually validate a citizen report and use data to validate that. So along a very busy corridor and intersection, there were drivers who were complaining that during the PM peak, they weren't able to clear the queue on the southbound left movement at this intersection. So the drivers were requesting a protected left turn on the specific movement, but they weren't getting it. It was a multiple phase or a two-phase operation in this case. So what the town of Milton did first was collect the data. So with the traffic lake system deployed, they also used our video detection. We added a separate left turn detection zone so we could kind of get some data back and figure out what was happening there. There's no protected left turn phase at this, it's just a left turn lane. And it also enabled us to identify issues using split trends to figure out the efficiency of how efficient this intersection was being in terms of throughput and moving vehicles through it. The second thing they needed to do after they collected the data was to measure the problem. So they used the split trend graph to look at, what time of the day is this occurring, and they found that to be 6:30 p.m., which is interesting because it's basically right in the middle of the rush hour or very busy commuter traffic day. How long is it lasting? They were finding that it was lasting about 2 hours until 8:30, which is very interesting because typically, in this part of town, the commuter time should be a little less than that, should end about 7:30, even 8 o'clock. And they wanted to see if this was a single day trend or if it was an anomaly. And what they found in looking at the data and measuring the problem is that it was actually a weekday trend, which meant that on weekends, when you didn't have that demand on the network from commuters and business traffic, it wasn't happening. And so interestingly, what they started looking at is they started looking at what the controller was doing at 6:30 p.m. And 6:30 actually lines up with the exact time of the end of the PM peak timing plan. So they had 2 time of day timing plans in place here, and 6:30 is actually when that initial time of day plan ended, and then the controller effectively went into free mode, so it was getting dynamic. So they were having an over allocation on the miner for green time, which was creating all of these efficiencies, and this was really uncovered through the data that they found. So the next step was really to implement a solution and then also measure the impact of that solution. So the traffic operations or traffic engineering team in this case was able to see that, well, hey, if we actually extend the coordination or the time of day plan to a constant cycle length through 8 p.m., that should cover, let's see what it does effectively as a bit of a test to see what would happen. And what they found is that the split failure count or the efficiency of the intersection, those split failures reduced by almost 45% along that corridor. And what that translates to is effectively people, travel time decreasing, and also people having more predictability with their commute. And if you look at this from a travel time perspective, there's a few unintended consequences that these changes to signal timing actually had. And the travel time index and reliability improvements for the entire corridor between that time of 6:30 and 8:30, which were previously the points of friction, were completely changed due to one simple change in the timing plan. And you'll see that the Thompson Road, the southbound movement on Thompson Road, the normalized traffic time index, or the time it takes, decreased by 30%, almost 30%. And very similarly with the northbound road or movement, it effectively decreased travel time did by 13%. So some pretty impactful gains there. So what I'd like to know is, this is our second and sort of final poll question, and then I'll hand the reins over to Sam to walk you through some really interesting insight that DRMP is doing with Escambia. But I'm really interested to see how you are currently completing signal retiming projects. So I'll ask Brent here to put up the poll question, and then we'll give you a few seconds to answer. And the answers could be anything from, you do them yourselves to you actually work with a traffic engineering firm, which we're starting to see a lot of. And you're going to hear one example of that next. Perhaps you don't do them today, which is interesting as well. Or maybe there's another reason that we'll look at together. So I'll give you a few seconds to answer that question, and then we'll take a look at the results. Okay, so we'll take a look at the results here. So very interesting. So it looks like many of the folks online here, it's sort of split between either doing them yourselves or even working with the traffic engineering firm. So that's very interesting. I think we're starting to see the latter become definitely more prominent and evident with a lot of our customers, where sometimes the reason you may not do them on your own is because you may not have the resources internally, staff-wise, to actually do them. So many of our customers are enlisting the help of the traffic engineering firm to help them through that. And one really good example, and I'll ask Sam to kind of introduce himself and see if that's actually something that Sam would agree with. So Sam, those poll questions. So we're starting to see a lot of folks on the line that are working with traffic engineering firms, to access this kind of ATSPM data. Does that seem kind of aligned with what you're seeing at DRMP?
I mean, yes, I would definitely say so. At least in our region of the country, we see a lot of consulting firms doing a lot of the traffic retiming studies and things in our area for sure.
Right. Well, good stuff. So that's really interesting. So I think what we'll do is we'll hand it over to you, and you can give us a bit of a background on kind of the project with Escambia County, and a bit of a background on you and your firm. So thanks, Sam.
All right, thank you. Hi, so yes, my name is Sam Campbell. I'll give you a little bit of information about myself. I went to Auburn University and graduated in 2012, and moved down to Pensacola, Florida, where I got a job with DRMP. I pretty much started out doing, we mainly did transportation design, major roadway reconstruction design and things like that. And that's when I started doing the design for our signals and ITS and those type of things. So I did that for a few years, and then we started doing some signal retiming with Escambia County and Santa Rosa County, and that's when we started really getting into a lot of the retiming and looking into different equipments and ATSPMs and things like that. There we go. All right. Just to give you a little information about DRMP, we're a consulting firm based in the Southeast, mainly in Florida. Our headquarters is actually in Orlando, Florida. We got mainly just in the state of Florida. We just opened up an office in Atlanta, Georgia, and on that map there, I believe it just shows 2 in the Carolinas. We recently just opened up a new office in the Carolinas. And go to the next. All right, so just give you a little background information on where Escambia County stands. Escambia County is actually the largest, most populated area in the Panhandle of Florida. We got a total of 190 traffic signals in Escambia County, and just give you some background on where our ATMS system and ITS system is. So we started out with just 18 signal pilot project, really, just to kind of get Escambia County's feet wet in the ITS and ATMS operating these traffic signals. So we first just had that 18 signal system, and then one of the things we were tasked with is to kind of bring in some new equipment and try out some things to get some more signals connected in the area and grow this system sort of as a interim type step, because Escambia County does have a master plan to build out the full system. It's actually a 2-county system, Escambia and Santa Rosa County. They got plans to build out a full fiber network and everything. But we've really been building on that original system we've got, and Miovision has been a big part of that. We've been using Miovision with their cellular capabilities to connect these signals and start operating these signals where we do not currently have any communications before. All right. Go to the next one. All right, but the particular corridor that or project that I'm going to be talking about today is actually on a county road. Escambia County decided to connect some of their signals and got DRMP to actually retime these signals, and we put Miovision all down. There was a total of 16 total signals. I'm kind of mainly going to be focusing on this corridor right here, this Palafox Street, because a lot of the others were just some isolated intersections where we did a lot of updating, but this was the main meat of the project here, where we were really trying to improve traffic flow through the area. They identified this as a very critical corridor, mainly because if you know about Pensacola, we really only have 2 major north-south roadways that go into the downtown area and connect to the interstate. And the one you see right here, this is actually 29 over here to the left of the signal we run. It's under construction, so we've seen a lot of traffic. In fact, we've seen traffic almost double on Palafox because all the traffic is moving over there while this is under construction, which will continue to be under construction for a few more years. So this was a very critical corridor to make sure that our timings are running as good as possible, and to really try to move some more traffic through it, because it's very critical at this point stage. The corridor, we see about 105,000 vehicles per week. That number has actually came close to doubled here in the last few years since we actually started this project, which was around the same time that the construction began. So that was one of the major things we were looking at. Another issue that we kind of came across in this area is there's a lot of schools in the area. So there's a school on almost every single one of these side streets. On 4 of these 6 side streets, there's a school. So we have a very big peak traffic right there when school gets out, between around the 2 to 4:30 or so. And that was one of the main things that we had some issues with and kind of worked through with these ATSPMs. We'll go on to the next one. All right, and now I'd like to talk about, just for a second, kind of I call it a traditional retiming project, just for kind of a lack of a better term for that. But kind of what I'm getting at here is this. I just want to give you an idea of what we typically do on a retiming project, and it's what we still do. This is still how we do all of our retiming projects. That's what we did on this project. But the reason I kind of want to go over this is because I want to kind of get into what additional things we were able to do now that we have these ATSPM capabilities on this corridor, in addition to what we typically do on just a normal corridor retiming project. So basically, we just start out collecting data. We put some sort of travel time collectors, Bluetooth or Wi-Fi, or just driving the corridor and getting your travel times. And we typically put out hoses to get our traffic counts. We use those 24-hour hose counts to kind of decide where we want to. What time of the day we want to get our turning movement counts and everything like that. So we start out with all our data collection, turning movement counts, hose counts, travel times. leave that out there. Then we start taking that data and building a model in some software. Usually we typically use Synchro mostly to create a model, and then we take all those signal timings and run it. We also use True Traffic a lot to kind of fine tune those offsets and come up with our timing plans. Then we go and we basically implement the timing plans. We program them all in, make sure that they're running correctly, monitor the traffic, but make sure all our timing plans are running the way we were anticipating, and make sure everything's running smoothly, basically. And we spend, and this is kind of where the ATSPMs kind of really came into play, and we saw a big difference in what we were able to do with them at this point, because we still implemented the timing plans. Well, for this many intersections, we would typically spend, a week or more out there just monitoring the traffic and making sure everything is fine-tuning all the timings and making sure everything is running how we want it to. Because of the ATSPMs, we were able to do a lot of this from the office. We implement them, make sure our timings were running smoothly and make sure it was running right. And then we were able to actually kind of do a lot of our fine-tuning and adjusting and everything from the office. And then we usually have at least a 90-day active arterial management where we respond to complaints. We or go check on things. If somebody calls in about something not working right, we'll go out there. If it's a maintenance issue, we'll let the county or the contractor know that they need to go fix something. Or if it's a timing issue, we try to fix it. Or if it's something that sometimes it's just a complaint that we just respond to the citizen and let them know what's going on and why it's doing what it's doing. All right, so you can go on to the next one. All right, so this is kind of where it was very interesting to me. We've used ATSPMs for a lot of monitoring and tweaking and things like that on a lot of corridors here in Escambia County. But this was actually the first project where we were doing a full-blown retiming and had the ATSPM capabilities. So it was very, very interesting to be able to use that, and not only to adjust our timings, but also to show that, show the difference we were making and with a lot of these things. And I just kind of go through kind of like I said, this was my first time doing this, so kind of want to go through what my steps were in how I used these ATSPMs to get the best timing plan out there. So I first started out with, the whole goal of this project was to increase our throughput on Palafox Street. So what I started out with was looking at our corridor congestion scan to try to identify areas that we could really focus on and make some improvement to improve our travel times through the corridor. And you'll see that in just a second. I'll get on to that in the next slide, I believe, to show you what I was looking at. And then once I identified these locations where we weren't quite up to the right speeds and things, then we started looking at our time-space diagrams and Purdue coordination diagrams, which you can see the Purdue coordination diagram over there on the right side. And so I was able to kind of identify and see where we could tweak it and change it a little bit to improve, to make some improvements. And what was very interesting was, we did identify some places we could have slightly tweaked the offsets and things. And once we did tweak those offsets, you could immediately see the speeds increasing on the corridor. And then once I kind of got all happy with the flow of the corridor and making sure everything was coordinated well and all our offsets were well, we started looking at each intersection individually, such as the split trends and our delay, And well, one of the big things we found, I mean, like I said earlier, there were schools on a lot of these side streets. Well, we had anticipated that, and had made our plans so that we had a school timing plan in there to try to push all this traffic off of the side streets. Well, we didn't anticipate some of the side streets that did not have these schools on them, and we would see a lot of split failures at that time of day, and we were able to kind of look through that and adjust our timing plans to give them a little bit more time on some of these other side streets to try to push all that traffic out before the PM peak traffic hit. One of the interesting things about delay, what we have always done in the past is pretty much our delay just comes from our model. It's kind of a theoretical calculated delay from our synchro model. Well, it was very interesting to me to get to compare this actual measured delay to our model and see if that's really what was happening out on the field. And in a lot of cases it was, and in some cases it wasn't. We would see a fairly large difference in what we were seeing. We'll go on to the next. All right, so here's what I was talking about earlier about the congestion scan. And so this is kind of where I decided to start off, just look at an overall of the corridor. And I kind of identified, you can see these red circles, I kind of identified these 4 areas as those where I wanted to focus to try to improve that travel time between those areas, and which would in turn improve the travel time along the entire corridor. So I basically took that and tried to focus on those areas and started looking at our Purdue coordination, our arrivals on red between those areas, and started narrowing down and trying to find where I could tweak it and make some improvement. Let's go on to the next. All right. So this was the time-space diagram before our retiming. Obviously, you can see there was no coordination at all out there on this particular corridor. So it was pretty ugly. But all right, go on to the next. And this is what we ended up with our final time-space diagram. So you can see much better coordination. You got some pretty large green bands going through there in both directions. This is a fairly directional corridor. You get mostly southbound traffic in the mornings and then northbound in the afternoons. So we kind of we favored one direction a little bit, but tried to keep it pretty coordinated in both directions. All right. All right, and see, this is an example of what I was talking about earlier, where late in the afternoons at this particular intersection, we were seeing before we were seeing a lot of split failures all afternoon and into the night at one of these side streets that the schools were coming out of. If you go to the next one. And then this is the after. So we improved that a lot. We had to give them a lot more time. In fact, we actually ended up coordinating it where when they came off this, because we had more traffic coming off this side street than we did on the corridor at this particular problem. This is the very south side. So we actually coordinated where this traffic that's coming off of the side street is hitting green up at the next signal instead of the actual Palafox going through, because we had more traffic on that one. Let's go on to the next one. All right, now I just kind of want to talk a little bit about, so once we kind of finished all of our retiming and everything, we started the active arterial management of the corridor. And with this, we started putting together these dashboards with just some information that we can show or give to Escambia County, and they can look at and have all the information there. Mainly just monitoring, making sure that the timings are continuing to run the way that they should, and that all the performance of the corridor is staying where it was, and also just to look at it, see if we need to make any adjustments or changes and anything like that. So we take these and we do a monthly dashboard on these corridors, and we're continuing that and turning these into the county where they can just kind of see that the timings are still running the way it should. If you look at, this one, you can kind of see that from at the very top, we kind of put the travel times along the corridor, and you can see that they've increased from the May to October. You can see there was a huge increase. Well, that's from the before and after we implemented the timing plans. But then also, if you look from October to November and then November to December, you can also see that was just from using the ATSPMs to fine-tune our timing plan. So there was a huge increase whenever we initially installed our timing plans, but then we were also able to use these ATSPMs to further improve that the timing. All right, keep going next. And this is just kind of the second page of that dashboard, and we have a front back dashboard where you can just kind of see the travel times throughout the day, and we do a lot of the individual intersection performance data on this page. And this is actually from a separate corridor where we're doing something similar. And I use this one just because it was just a good example where we kind of found several things to change and to improve the corridor. Because if you look at this one and you look over on, say, US 98, we saw the split failures went up 100%. Right there. Yep. So we finally went out there and we kind of identified, and if you look at Chiefs Way, that one also went up. Well, both of those two roadways are going into Corey Station, which is the military base, and they had actually changed whether they closed a couple of their gates and were sending all the traffic out a different way. Well, we noticed that on here when we were putting together these performance measures, and we knew something had changed out there. And we come to find out that, yes, they had changed their gates. They were sending everybody out a separate gate, changed the traffic patterns, and obviously we were having a lot of split fares. We had an increase. But we caught that before we started getting any complaints, and we're able to go out there and correct that and adjust it. And then, so that was a pretty interesting one. Another one, if you look at, obviously, if you look at Gulf Beach Highway, you can see that improved a lot, but there's still a whole lot of split fares. Well, that was actually because the CPU and the detection camera went out, and the month before, so we had we're having a split failure on every single phase all day long. Well, that got resolved here. This dashboard's from December. That got resolved there, and you can see it went back up a lot. But the interesting thing about that is we can use that information to kind of prioritize our maintenance and where, like, for instance, this one, that needs to get fixed very quickly because you can kind of show how much delay you are increasing by that CPU being out. And you can use that data to kind of prioritize where you need to get that thing fixed quickly. All right, and down here at the bottom, go ahead. Yeah, down there at the bottom on the maintenance data, we also just kind of include that just to so that Escambia County can see if they're spending a whole lot of time doing maintenance on a certain intersection or getting a lot of problems at a certain intersection. We may have something wrong out there and can get out there and fix it. And so that we just kind of include that data as well, just so they got an idea if they got a problem that needs to be addressed. Go on to the next one. All right, so yeah, in conclusion, with this particular project, we we ended up with about 1,200 vehicle hours per week in time savings, which and then the 3,400 gallons per week in fuel emissions reduction. And we basically just took that into a benefit cost and multiply that by the pay the value of time and your cost of gas, and came up with a cost savings of $7.8 million for the life of this project, which we typically say a project lasts anywhere between 3 and 5 years before it needs to be retimed again. For this project, we used 3 years. But one of the things that I've kind of noticed and seen with these ATSPMs is that these retiming projects, you could probably extend that a lot longer if not because you're constantly adjusting and changing to those traffic pattern changes instead of just putting your timing plan out there and letting it run for 3 to 5 years till the traffic patterns have all changed. You're constantly keeping it up to date by adjusting those timings as the traffic pattern is changing. So I think you get a much longer lifespan out of these timing plans when you're using these ATSPMs. And we finally ended up with a benefit to cost ratio of about 81 to 1. Which this is a very high one. A lot of it's the reason because we went from a non-coordinated system, had no coordination at all, to putting coordinated timings in it. So you're going to get very good results whenever you do something like that. I mean, obviously your improvement depends on how bad it is in the first place. So this was a very good project that we saw a pretty large improvement, and we've gotten a lot of confidence. People who actually drive the corridor have been very happy about it, I think, that's about all I've got.
So that's great, Sam. This is Matt here. There was actually I really appreciate you sharing that case. And for those of you online that are interested in learning a bit more about Sam's work at DRMP with Escambia County, we've created a case study that kind of covers and goes into a greater detail of what Sam just describes here in terms of his process for collecting data and how they turn that into meaningful insights and how they actually use that to propose some recommendations. Before we kind of get into the rest of to close this and wrap this up, Sam, there were a couple questions that kind of came in that I wanted to get your thoughts on. The first is one from Heather, and I'm just going to back up a few slides. So she was really interested in the time-space diagram and was curious as to what type of equipment is needed to get this information. And I thought I'd let you answer just based on the data that you gathered from this project to see how you went about, like what equipment you sort of deployed in order to gather this information.
Oh, well, yes. I mean, this came from the Miovision and, well, I guess the Miovision widget controller. It gives you these time-space diagrams because, I mean, basically it's for sitting there recording when the signal goes yellow, when it goes red, when it goes green, and you've got the location of the signals in it that is already programmed into there with your map. So basically, yeah, you just log into the Miovision, and that's where this came from.
Right. So yeah, I guess what you would need is equipment that would effectively collect detector hits, like stop bar actuation or activations, probably some phasing information too as well, that would go into all of this. And that I think is the nice thing where, those sort of data points in isolation are a bit noisy. They don't really provide you with a lot of actionable intelligence, but when you start to combine them and present them in a way that makes sense, you get a really nice, time-space diagram where you can look at a corridor and visually see, I mean, before a timing plan is implemented and then after how properly timed signals effectively look along a corridor. And that's pretty telling, I think, in that case. There's another question that came in from Rodney here, and it was around split failures. And so I figured I'd let you, Sam, answer the question of, first of all, like, how do you get information from this? How do you kind of understand what this is? And even above that, what is a split failure?
All right, so like I said, this came from the Miovision as well. Basically, how it's calculating that split failure is you got your stop bar detection there, and when when the light goes green, your queue starts going and starts going through. Whenever the light goes back red, whenever Miovision does, whenever a vehicle is back on that detection zone within 3 seconds. That's
Correct.
what they record as a split failure, because you know that if it goes red and a vehicle's on that detection zone within 3 seconds, then your queue didn't clear.
Exactly. So a way to think about this too, Rodney, in this case, is you can almost think about a split failure as a measure of efficiency or throughput for an intersection. So if a vehicle is not able to clear the phase, that means you've got queuing or effectively congestion that's starting to be created. And what Sam did in this case was his work with analyzing the ATSPMs was able to kind of go in and understand where efficiencies could be unlocked just by simply proposing some simple changes to the timing plans. And if you look at the before and after, basically before you see these red bars, that means that we're detecting a split failure in that case. A split failure would mean that specific intersection is not able to clear, so you're getting congestion. After the timing plan change, you can see the green, an acceptable level of capacity or efficiency, as well as spare capacity, I think is the most interesting thing here that has been created within the system. So I think that's kind of interesting as well.
Right.
So
and also, essentially, like if you say you got to look at the split failures for conflicting, phases too. So if you're, looking at phase 4 and there's a lot of split failures on phase 4, well, then you got to go also look at phase 2. If there's a lot of split failures on phase 2, then you may not can add time, but if you kind of got to look at the other phases, and then if you see some that have plenty of spare time, kind of take a little bit of time of that and move it over to phase 4 or whatever it is that you're having the split failures on.
Right. Yeah, exactly. That's awesome. Okay, appreciate that, Sam. Thanks a lot. So hang around there, as just in case there's a few more questions that sort of come in as we go, and then I'll walk us through just a few items to round us off here and close us up. So one thing I wanted to, because there's a lot of questions around what's a split failure, how do you calculate that, what data is required to do that, and kind of from the onset, this is something that we identified with our customers in general, is that there's a lot of folks that are familiar with ATSPMs, but they really don't know where to start. And we actually created an ebook called Clear Signals. And this is something that describes those 3 core use cases: maintenance, operations, and optimization for ATSPMs. We've created it in a way that's simple to understand. It gives you that starting point of where to start, like what you need to do, what to consider. It's extremely visual. So there's more than 80, there's almost 100 figures in total throughout the yearbook. So, it's very graphical, very easy to understand. And more importantly is it's example centric. So I think rather than being sort of an academic type of taking an academic approach to it, we're actually providing you real world examples like what DRMP has done with Escambia County of more than 20 practical use cases and examples. This specific ebook is focused on Miovision functionality, but you can get an idea of the types of data that you need in order to generate these metrics. And it goes through, how do we actually do, before and after on split trends or split failures? What is a Purdue coordination diagram? What's a random arrival count? All of these things. And so, it provides a really nice way to sort of like action that intelligence. Now, the way that you can access that ebook is actually if you hit that link that's on there, and the link is actually, we're going to put that in the chat for you as well. Where if you go to ATSPMs.com, you'll be able to download your own copy of that ebook, and you can get started on your own. The other sort of element I wanted to walk through that we talked about in the poll question is, how can you actually put what DRMP is doing here, active arterial management, and using ATSPMs, how can you put that to work for you? The very first thing is downloading that ebook and understanding, what ATSPMs are, how you collect that data, how you actually use the analytics to do that. The second is, Miovision's here to help. So we've got expertise in this area specifically. We have on-site traffic engineers that analyze corridors, just kind of spend their days analyzing this type of data and information. And the last element is contact your local traffic engineering firm. So if you don't have the resources or ability to do this type of analysis in-house or internally, firms like DRMP are available and ready to help you out, with any of your consulting on your traffic engineering processes or strategies that you might need. So the ebook is definitely a great way. I think that you can get real world examples of that. So before we get into questions, I wanted to actually introduce. We've got a promotion here where for the next 90 days we have the ability to so if you hit this link that Brent is just going to put in the chat there, it's going to take you to a landing page where we're just going to ask you a question of, what effectively is there a way that you're going to that you're struggling with traffic challenges and you don't know where to start and what that is, and there's an opportunity for your agency to work directly with Miovision to receive a 90-day pilot program where we can deploy a similar type of methodology and analysis to your agency to help you understand how progression is moving through your city, but foundationally really help you solve those challenges, those foundational challenges with how you're looking to improve maintenance operations and even optimization. So I will close by just looking at some of the questions. We'll take the next few minutes here for some questions that we haven't been able to get to. So let me just see here. So potentially a question here for Sam. So it's a question from Marta. So initially, right after the implementation, how often did you monitor the corridor and the results of those corridors?
Hi, well, so immediately after probably the first week or two, I was monitoring it every day, and I would spend probably a couple hours every day just looking through the data and trying to come up with some ways to improve it and everything. So, and initially those first week or maybe 2 weeks, it was pretty much every day, a few hours a day, looking through it. And then after that, once we started kind of the active arterial management, it became more of I'd spend 2 hours a week just looking through the data and everything, and responding to calls and things like that. So yeah, initially I would spend a few hours every day, and then it kind of became every week I'd spend a few hours.
Excellent. There was another question here about explaining the before and after diagrams. I think Sam had answered that. Anything that is sort of related to a specific ATSPM, what I'll ask is that you hit that ATSPMs.com site and actually look at the ebook. There's a lot of really good examples that the ebook kind of walks you through in terms of how to understand what those ATSPMs are and how to access that data. Okay. So there's actually a comment on here. So there's a couple of folks that are on the line that have downloaded that ebook. The ebook is great way to see actual examples. So thank you very much for that, Heidi. We've put a lot of work in, especially with your specific agency, to provide some examples there. So appreciate it. And then the last question here that's come in is, can you get this information with Miovision data link? And so, yeah, really good question, Heather. So for those who are unaware on the line, we also have a portable traffic data collection system called, really the product is Miovision Scout, but our solution there is the data link system. And what that's really used for is to collect turning movement counts. It's used for spot studies, pedestrian, cyclist counts and volumes, as well as travel time. So the system itself can collect data sort of on in shorter time periods, some of those inputs. What you're going to be missing is the detection hits, the actuation, the pedestrian call button information, those other data points that you actually need to combine into those data sets. So while volumes and turning movement counts and those sorts of things are important inputs into the ATSPM framework, or landscape, you actually, to get a complete picture, you need a few more metrics that the traffic link system is able to provide. And to give a bit more background on how traffic link works, so it is a system that, first of all, as Sam kind of mentioned, will provide connectivity at the traffic cabinet if it doesn't exist. The SmartLink system will also integrate into all of the existing cabinet elements, such as your traffic controller, your MMU, any detection. If you have loops or any other detectors that are in the system, we can integrate that. And that's the data that we capture to provide some insight on. We also have a video detection system called Miovision, part of Miovision Traffic Link. Our SmartLink is connected to our SmartView 360 camera as well as our SmartSense. And that actually is doing the counts and classification in real time using computer vision. So in scenarios where you don't have detection, we do have a system that will provide you with those metrics. But really, in order to do that, you need a complete system. Let's see if there's anything else that came in here. Okay, it looks like we've covered most of the questions here. So what I'll do is one last question that came in here from under the wire here from Jonathan. We'll take this one and then we'll close the webinar because I think this is a really good one for Sam. So a question around schools. So in this corridor, since schools were a concern, how was pedestrian traffic designed into your analysis, your ATSPM analysis?
Well, actually, on this particular corridor, we don't have a lot of pedestrian crossings at these intersections. In fact, their schools are actually a little ways down these roads, and there wasn't any pedestrian crossings, I don't believe, on any of these intersections. I'm looking real quick. Yeah, there are no pedestrian features on any of these particular corridors.
I think that makes sense too, considering that you said the initial sort of objective was to maximize like progression and efficiency along the corridor. So I think that makes sense, and it also makes sense too if the schools themselves are actually set back, if they're off the arterials, that they do feed into Palafox Road, but it's not something where they're directly crossing across those intersections there.
Right. Yeah. There's very little pedestrian traffic on this particular corridor. There's not a lot of residential. The schools are a little ways back off the road.
Excellent. Well, appreciate your time today, Sam. Thanks for your insightful, information there and real world examples of how, DRMP is using ATSPMs to actually provide some really meaningful results, I think, to Escambia County. So I want to thank you for joining the presentation today. For all of the participants, the recording will be made available shortly after this as well. So you'll have a link to the recording as well as the DRMP case study that describes sort of Sam's process in terms of how he's gone about using ATSPMs to affect some change there. So you can download that case study. But with that, at the top of the hour, I'll close the call, and thanks everyone again for joining today.